Good morning, children. In this video, we are going to discuss about crystal field theory. It's a very important theory, crystal field theory. So, whatever the limitations present in the valency bond theory, which are rectified by crystal field theory, isn't it? So, crystal field theory is very, very important for us. What is this crystal field theory? Let me see. This theory, the electron pairs on the ligands. So whatever the electron pairs which are present on the ligands like this are viewed as point negative charge. They viewed as point negative charges. So lone pairs are viewed as point negative charges and that interact with the d orbitals like dxy, dyz, dzx and dx square y square dz square of the central metal atom. So ligands are interacting with d orbitals. The nature of the ligand and the tendency towards covalent bonding is ignored. So what type of the nature of the ligand and the tendency of covalent bonding? You are just ignoring this one. For example, you take d orbital contains dx square, y square, dz square. Now these two orbitals are along the axis. They are along the axis. And when you observe here what happened, dyz, dzx, and dx. They are between the axis. They are between the axis. Okay. Next, ligands. Just now we discussed. They are taken as a point charges. At the corners of the octahedron affect the variation in the d orbitals differently. If you see what happened, octahedral structure, when you have coordination number is equal to 6. In that case, ligands when approach, means what happened, like point charges are approaching d orbitals. Now this is along the axis, along the axis, along the axis. Between what happened, isn't it? They're actually x5. So now here, if you observe what happened, dz square. In this one noted actually for us, dz square. Now dz square present where? Along the axis. It is present along the axis. Along the axis. Now here, dx square y square present on here. Dx square y square. It is also present again along the axis. Along the axis. Okay. Now, what about this one, xy? These are present. These three are present. If you observe what happened, they are between the axis. Between the axis. Okay. So they are present between the axis here. So which one present? dxy, dyz, dzx. They are present between the axis. Dz square, dx square, y square. They are present along the axis here. Now let me see how the splitting will take place. Now lone pair contains the electrons. So the repulsions between the ligand lone pairs, the repulsions between the ligand lone pairs and the d orbitals, which takes place, and because of this, what happened? The d orbitals, the 5d and Eg actually. So whenever these ligands are approaching the d orbital is getting splitting into two ways here. Let me see that one. See now I told you dz square, dx square, y square, both are along the axis here, and these are actually between the axis. Now what happened? These will convert into TTG, T2G, triply degenerated. EG means what? Doubly degenerated. So what happens? These three will come aside. These three will come aside, and these two will come other side. Okay. Let me see this one how it is taking place. See, this is the energy. Now this is the d orbitals. One is dxy, isn't it? dyz, dyz, dzx, dx square, y square, and finally dz square it is. Okay. Next again, same thing it will be dxy. They're getting some energy when the ligand is approaching. Their energy what happened? Increased here. Yz, zx, dx square, y square, and dz square. Now suddenly what happened? Whichever along the axis, these are along the axis here, they are getting more energy. Their splitting means they're deviating. The repulsion is more. They move what high energy. They move what high. Now what about the remaining these three? These are what actually between the axis here. Their energy decreased here. They split less here. They come here down actually. They are coming down actually because they are between the axis and these two are actually along the axis. Whichever along the axis, they undergo more splitting takes place here. Here more splitting takes place here. Here less splitting takes place. That means what happened here? The 5d orbitals are getting what splitted into two ways. One is called T2g, other is called what EG here. Okay, in this way. Now the splitting energy, the crystal field CFSE, crystal field splitting energy, if you observe for this one. Now for this, if you observe for 2Tg here, how many total orbitals are 5? Out of 5, 2 are what happened? Getting more energy. Therefore, 2 by 5 delta O. This one we get total 5, out of which only 3 are getting what down here. So 3 by 5. O for what? Octahedral. This is for what? Octa. O for what? Octahedral. Octahedral. Delta is nothing but splitting energy. It is splitting energy. It is, okay. In this way, what happened? X square, y square, dz square will undergo more splitting, whereas dyz, dxz, dxy will undergo less splitting. T2g means what? Triply degenerated. Dxy, dyz, dzx will call T2g, and dx square, y square, dz square is called what? EG actually. Now let me take tetrahedral. Tetrahedral will get reverse manner. It will get a reverse. If it is tetrahedral, that means coordination number is equal to 4. In that case, what happens? The splitting takes place reverse manner. Okay. Now it will be inverted, means reverse manner. Now what happened? T2g will undergo, this one will undergo more splitting it is. This will undergo less splitting now. So it will get like this here. We get like this. Tetrahedral manner, what happened? We are going to get what actually EG will have here. EG will have down actually. T2G will get here actually. So dx, y, dyz, dzx will come above, whereas dx square, y square, dz square will come down actually. Isn't it? This is happening in very tetrahedral. So the energy difference between these two seta is called what? Crystal field splitting energy. So for tetrahedral, delta T we can call this one. T for what? Tetrahedral. Octahedral, O for what? Octahedral. So what is the relation between the splitting in tetrahedral and splitting in octahedral? That is always equal to delta T is equal to 4 by 9 into delta O. This is what important for you. You need to remember this equation, very important, delta T and delta O. For example, in most of the cases, they are giving delta O values and they're asking the delta T values here. Magnitude of crystal field depends upon the field produced by the ligand. So if it is strong ligand, okay, the splitting will be higher here. So it depends upon the ligand and also charge on the metal. So if you have more charge, for example, Fe plus 2 and Fe plus 3. Now which will have more splitting? Fe plus 3 will have more splitting. Some ligands are able to produce strong fields, in which case the splitting will be large, whereas other produce weak fields, consequently results small splitting. So very simple, weak ligands will split less small by the weak ligands, okay, whereas strong fields, strong ligands will give strong splitting actually. So in generally what happens, how to know this, which is strong ligand and which is weak ligand? By using a spectrochemical series, we can easily identify which is strong ligand and which is weak ligand. So if you observe what happened, so after the water, whatever the ligands were having, what they are what strong ligands, and before they are what actually they are weak ligands actually. Whatever here, these are actually what weak ligands. You can easily take. These are what weak ligands actually, isn't it? These are actually what weak ligands here. So when you have what happened, carbon monoxide, Cn minus, NO2 minus, ethylene diamine, ammonia, generally what happened, they are having strong splitting. They are strong ligands. The pairing of electrons will takes place when you have Strong ligands, isn't it? In the last video, we have discussed that one in the VBT theory. Strong ligands pairing the electron, weak ligands do not pair the electrons here. Electronic structures of the complex according to CF theory, crystal field theory, it depends upon whatever the configuration. We are writing some configuration or D1, D2, that depends upon splitting only. So if you have strong ligand, what happens? The electronic configuration will change. If you have weak ligand, electron configuration will change. So that means electronic configuration depends upon what actually, whether you are taking strong ligand or weak ligand, because the strong ligands are splitting what more actually. So in octahedral complex, three orbitals are having lower energy. What are they? T2G orbital. What are the T2G orbital? DXY, DYZ, and DZX. These three are having what? Lower energy. And high energy by the two orbitals. What are the EG orbitals? What are the DX square, Y square, and DZ square? These are having what? More energy. Where in the octahedral complex. In tetrahedral, you are getting the reverse manner. And we have, whenever you're filling the electrons in the T2G and EG, we have to follow which rule? Hund's rule we have to follow here, isn't it? We have to follow what actually? Hund's rule. And electron occupy a set of orbitals of same energy, one at a time with their spins are parallel. You have to follow the Hund's rule. After the Hund's rule is nothing but after half filling only, you have to pair the electron. For example, you're having like this. You're having like this. Now you got four electrons. T2G is having what actually? Four electrons are there. Okay. Now you have to fill electrons like this. 1, 2, 3. Now fourth electron we have to fill. You can't fill this like. You can't fill like this. It is not correct actually. This is the wrong way. So once if you half fill, then only you have to pair the electron. This is what actually understood. The complex having three d electrons, d1, d2, d3. Each electron can occupy separate orbital in the lower set as shown below. Something if you have d1 configuration. So T2G occupies how, let me see here. Okay. If you have d1 configuration, how it occupies here. Now you see only one electron is there. This is T2G orbital. This is the T2G orbital. Only one electron is there. In EG, this one. This one is the EG orbital. So you have only one electron. So the electron will enter where? In T2G only. Now you have two electrons. Now electron will enter like this here. T2G, 2 it will be. Next, if you have three electrons in the d orbital, D3 configuration. For example, you have D3 configuration. So how many electrons you are having? 3 electrons. Now fill that 3 electrons in Hund's rule. EG will have no electron because only availability 3 electrons. This is called T2G3. Next, what happened for D4 complex? All the 4 electrons get occupied at lower set and it will be paired also. Now let me see that one actually. Let me see this one. Okay. This is, we are discussing that. Let me this one. If you have T2G4, what happens here? T2G4. I told you just now. I told you this one. T2G4. This one is what? EG. This one is what? This is which complex? Octahedral complex. Now you have how many electrons? D4 electron is there. Now how to fill this one? 1, 2, 3, 4. So this will be T2G4. EG will be 0 here. For example, I want to fill D5. I want to fill what? D5. And again, what I have to do? Again, T2G. Again, what happened? Sorry. EG. So I need to fill how many? 5 electrons. 1, 2, 3, 4, 5. T2G5, EG0. I want to fill D6 electron. How to fill this one? Now again it is T2G. 1, 2, 3, 4, 5, 6. Now EG will be 0. Now when it takes place if it is strong ligand. If it is strong ligand, we need to pair like this. I will show everything in a slide here. I will show everything. If I take what is weak ligand, first of all, I will take a weak ligand. How it takes place in presence of weak ligand like water, chlorine, bromine. How the electrons will take place. D1 in octahedral complex. In octahedral complex, you have D1 configuration. You have to fill like this. This is what? T2G. This one will be H. You have to fill here. The configuration will becomes here T2G1, EG0 here. Now if you have D2, This is D2. And here it also you are having Eg and T2G. You have to fill the two electrons like this. 1, 2 like this. This will be T2G2, Eg0. Next, if you have D3, then again T2G, and this one will be Eg. Now I have to fill electron 1, 2, 3. Therefore, T2G3, Eg0 configuration. If you take what D4, D4 if I take what happen, okay, and it is what Eg here. This one will be the T2G. 4 electrons you are having. Now how to fill this one? 1, 2, 3. Fourth electron you need not to fill in T2G. Where you have to fill it? Eg. Why? Because this is weak ligand you are taking. For weak ligand, splitting will be less. There will be very less splitting. That means the energy difference, isn't it? Splitting less, the energy difference between T2G and Eg will be less. Eg will be less. In that case, what happened? The fourth electron where we are entering in Eg orbital. So in this case, T2G3, Eg1 we have to write here. Now if I take what D5 now, if I take D5, okay, this one will be again T2G, Eg. Now I have 5 electrons. How to fill? 1, 2, 3. The weak ligand, no. Therefore, splitting will be less. The fourth electron will enter here, and the fifth electron will enter here. This will be the configuration here. Now I have to write here T2G3, Eg2 here. Next, D6. D6. How to make D6 here? This will be the T2G, and this one will be the Eg. Now 1, 2, 3, 4, 5. Next, the sixth electron we need to pair like this. The sixth electron I am pairing here like this. The sixth electron I am pairing here. Now it will be T2G, 4, Eg2 here. Next, D7 if I take, what happen? D7 if I take here. Okay, D7 I am taking here. Now again take Eg here. T2G and Eg. So 7 electrons we need to fill. 1, 2, 3, 4, 5, 6 is pairing and 7 also getting pairing here. So T2G how much here? 5. Eg will be 2 here. Next we'll take D8 configuration. D8 configuration. This will be Eg and this one will be the T2G. So 8 electrons we need to fill here. 1, 2, 3, 4, 5, 6. Sorry, you have to fill like this. Sorry, you have to fill like this. 1, 2, 3, 4, 5, 6, 7, 8. Now all T2G paired electrons here. How many there? T2G 6, Eg2. Next, what happened? D9 configuration. D9 configuration. 1, 2, 3. Next, what happened? Now 9 electrons are there. How to fill? 1, 2, 3, 4, 5, 6, 7, 8, 9. This will be T2G 6 again. This will be Eg. Finally, we'll take D10 configuration. D10 configuration. In D10 configuration, how to fill this one? Same like this. Okay, this will be T2G. This one will be the, how to fill the electron? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So totally it is what happened? Filled completely. T2G6, Eg4. In this way, we need to fill what type of ligand here? Isn't it? The ligand is what actually? The ligand is weak ligand. If you get weak ligand, the splitting energy between these two is what happened? Very less. Okay, the splitting will be what? Less. In that case, electrons, isn't it? First half fill in T2G, then half fill in Eg, then pair in the T2G, finally pair in where? Eg orbital. But if I take what strong ligand, what happens here? If I take a strong ligand, what happens here? If I take what a strong ligand, what happens here? Let me see. Strong ligand I am taking. I am taking a strong ligand. Now, in this case, what happened? Let me see. In the strong ligand, what happens? Splitting will be more. Splitting will be more. Splitting energy will be more. In that case, what happened? The energy difference between E2G and EG will be what? More. Will be more. Isn't it? It will be more actually. So in that case, if I take D1 configuration, same thing we get, no problem. If you take strong field, not much difference we get here. Now the energy difference is strong here, more here. So I have to fill like this. T2G 1, EG 0. If I take what D2, if I take D2 like this here. T2G and this one will be the EG. Energy difference is what? Strong here. So 1. Next what happen? I will take D3. So 1, 2. T2G and EG. So 3 electrons we need to half fill like this. This will be T2G3, EG0. This will be T2G2, EG0. Here. If I take what D4 configuration, D4 configuration, now what happens? Again, T2G, okay, D4, how to fill this one? 1, 3. The fourth electron we can't enter here. Don't enter here. Enter here only. In T2G only. Why? Because between these two, large energy difference is there. Large energy difference is there. That is the reason pairing of electron must be done in T2G before filling the EG here. So this is very important. So T2G4, EG0. So in that case, D4 is differ when you compare with what? Weak ligand. So for weak ligand and strong ligand, D1, D2, D3 will be same only. But D4, it will be different. If it weak ligand, D4 will have T2G3, EG1. For strong ligand, D4 will have T2G4, EG0. Now let me take D5 configuration. When you have D5, what happen? You can take like this. Okay, this will be the T2G. This one will be the EG actually, right? So how to fill the electron? 1, 2, 3, 4, 5. So T2G5, EG0. Because large energy difference, therefore electron enters here not. Where it will enter? T2G orbital, D6. Again, EG. So 6 electrons we need to enter like this. 1, 2, 3, 4, 5, 6. This will be the T2G 6 and EG will be 0. Now let me take D7 configuration. D7. Now this will be the T2G. This will be the EG. Now D7 means again 1, 2, 3, 4, 5, 6, 7th electron is getting in the EG. So T2G 6, EG 7. Now D's 8 if I take D8. T2G and EG. Now 8 electrons I need to fill. 1, 2. We have to follow the Hund's rule. 2, 3, 6. Next what happens? 7 and 8. Now T2G 6, EG 2. Now we'll take D9 configuration. D9 configuration and T2G and EG. So 1, 2, 3, 4, 5. Now, sorry, you can't enter here, no? Sorry. 4, 5, 6, 7, 8. Ninth electron is also in EG. So T2G6, EG. Finally, we'll take D10 configuration. This one will be the EG. This one will be the T2G. So to enter 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 here. So total it will be TTG4 and EG6. Now when you observe for strong ligand and weak ligand, D10 will be same. Okay. Next after what happen? D1 is same, D2 is same, D3 is same. Remaining will be different. Okay, depend upon the strong ligand and weak ligand. D5 configuration depends upon D4 also. D4, D5, D6, D7, D8, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9. In this also they are same only. D9 also will be same. Okay, because you are getting like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8 also. These are what same. Whether whatever it may be strong ligand or weak ligand, these are getting what same only. Why? Because how you are filling in the weak ligand in the D8 actually 1, 2, 3, 4, 5, 6, 7, 8. Okay, ninth electron. Ninth electron, we are filling like the same thing we are getting actually. See, so these are both the actually what filling the electrons in the T2G and EG orbital, isn't it? In this case, the repulsions due to pairing of electrons will be less in their where octahedral splitting energy here. So on the other hand, small splitting will be there for weak ligand. So if you take weak ligand, the splitting will be small. So the electrons will enter first T2G, then EG, then only they will get pairing of electrons. But in the case of what happens strong ligands, the splitting will be more. In that case, first of all, the electrons will completely fill in T2G, then go to what? EG. The thing we are just actually explaining. So the pairing of electrons will occur only after the 5 orbitals are singly filled. Okay. So everything we are completed, everything. Just now we completed it. So in this, the actual configuration adopted by the complex that is decided by the relative splitting energies and pairing energies. So this is actually when splitting energy is more at actually splitting is more what happened, pairing is taking place. Pairing of is less, we have weak ligand. Splitting is more, then it will be strong ligand actually. Already we discussed this everything by taking the samples actually. Okay. This is a D4 configuration. So splitting energy is what high. So fourth electron is entering where actually here. The fourth electron is entering here actually. Okay. And splitting is what small. The fourth electron is entering where here. Here it is entering. Okay. So that means this is in the presence of strong ligand. Strong ligands, if you observe, the fourth electron is getting paired in T2G orbital. You take weak ligand, what happened? The fourth electron is entering in the EG orbital because the splitting energy is what? Less in this case. Strong field ligands forms low spin complex. See, so you have less number. So strong field, this is strongly field. So how many lone pairs you are having? 2 lone pairs. You have weak ligand here. How many lone pairs you are having? 4 lone pairs. So when you have more lone, when you get more lone pairs actually, whenever if you have weak ligand, okay, you are getting more number of lone pairs actually. More number of unpairs. More number of unpaired. More number of unpaired electrons. There are how many unpaired? 4 unpaired electrons. Here how many unpairs? 2 unpaired electrons. So when you have taken strong ligand, less number of unpaired electrons are getting. Therefore, it is low spin complex. When you are having weak ligands, you are getting more number of unpaired electrons. You are getting what? High spin complex. After the following is strong ligand. Definitely what happens? Cn minus is stronger than what? Carbon monoxide. And but B and C are what generally called as strong ligands. These are the weak ligands. These are also weak ligand. The following is a weak ligand. Cl minus, even I minus also weak. These two are what? Weak ligands actually. So these are both